Okay. Good afternoon, everyone. Welcome to the second part of the talk by the Professor John Hay on the Hodograph as a visual aid to study the charged particles in collisions.
Thank you. Thank you. Thank you very much, everybody, for attending. This afternoon, I just need to repeat some of what was covered last time, just for continuity's sake. I'll mention that the Hodograph was a contribution to classical mechanics made by some very celebrated 19th century physicists and mathematicians, but it was applied exclusively to astronomical problems, where the interaction is attractive and the particle is generally a bound particle. And my interest was to try and take these ideas and see whether one could use them for charged particle interactions. Now, one would immediately say I'm taking something from the purely classical regime and applying it from the macroscopic to the microscopic world. And in order to do that, one has to think of validity criteria, which we were discussing in under what conditions can a wave packet simulate a classical particle. The idea was then to try to adapt the treatments that I had read and find out whether, in fact, they were adaptable to the cases where the particles are free and interact. And we're dealing with two particle interactions between two particles, and for simplicity, we'll consider the center of mass frame. We have a fixed center of force or interaction, and particles scatter from that. Now, the Hodograph, just as a reminder, the meaning, this was introduced by Sir William Rowan Hamilton, the famous Irish mathematician and physicist, in 1846, actually, December 1846. And the origin, I pointed out last time, were these two Greek words. Now, graphe is, of course, the origin of our graph. When we draw graphs, we're using a Greek word. They're adapted to English. But if you were talking to Aristotle, you would say Hodographe, the drawing of a path, genitive. Now, what the Hodograph is a type of trajectory where one follows the velocity rather than the coordinate. So we have the coordinate, velocity, tangential, the acceleration. But in the frame of the Hodograph, the coordinate is effectively, r prime is the velocity of the particle, tangential to which one has the acceleration of the particle. And it's this motion in what we would now call velocity space that constitutes the Hodograph. Now, this was one example. Now, when I say following Maxwell's construction, we discussed last time the origin, it's Hamilton's origin, Hamilton of Hamiltonian fame, Hamilton, Jacobi fame, and many other things. James Clerk Maxwell was writing a book called Matter and Motion, whose aim was to introduce abstract scientific concepts to working people with very little mathematical background, which amused me to see what he assumed as being very little mathematical background. But he evidently, I think, felt somewhat dissatisfied with Hamilton's treatment in the sense that it's perhaps, I'm imagining, it seemed unnecessarily complicated. And it certainly is, to my mind, difficult to read because there are no drawings in the paper. An extensive amount of geometry is described verbally, and he drew his conclusion. And I could imagine to myself that Maxwell thought, well, there must be a simpler way of doing this. Let me do it in my way. But it was again for the same problem, the astronomical problem, actually gravitation applied to a planet moving around the sun. So I wondered whether we could take the approach of Maxwell and try to apply it to a case where the particles are free, the potential either attractive or repulsive. And this was a construction. I pointed out that this happens to be a special case for the drawing in which the eccentricity value, this value epsilon equal to 2, and that is the angle between the asymptotes. The half angle of 60 degrees means that this particular hodograph passes through the origin. That's a special case. But this is the drawing. We have the particle traveling along the hyperbola. That is the center of force over here. One draws a circle around this is the focus of the hyperbola, the conjugate focus over here, and the A value, that's the A over there, the distance from the center, symmetrical center, to the point of closest approach. But one takes that distance A, one doubles it and draws a circle. And what we saw last time as a proof is that we have a distance, if we measure from the conjugate focus, this S prime U, which is proportional to the velocity of the particle, but at right angles to it. That's the difference between Hamilton's construction and Maxwell's. So you have to multiply this by a constant factor in order to get the value, the absolute value of velocity. But this vector, as the particle moves around the trajectory, the point U moves opposite to R. Here you have the point of closest approach, the largest value of the speed. But the big difference we discovered was that the hodograph, whereas it's a complete circle for bound particles, for free particles, it lies on the circle, but is not a complete circle. So in this case, we draw the two tangents, and the hodograph covers the arc of the circle from the one tangent to the other. That's the tangent drawn from the conjugate focus to here or to here, and that describes the passage of the particle, which escapes again, comes from infinity, interacts, escapes. These are just the standard formulae. That's the half angle between the asymptotes, phi upon 2. Now this is a very nice little construction which I didn't find in I haven't yet found in any of the books on analytical geometry. You just take an asymptote and drop the perpendicular from the focus, and that happens to be equal to the parameter B. I haven't yet found it in a book. I'm sure there are books in which that's found. And this quantity H is something that these great scientists were very fond of, because it connected Kepler's second law with conservation of angular momentum. Now, the magnitude of this H is twice the area swept out, let's say, by the planet per unit time. It's in the orbital angular momentum divided by the mass. So that's why they like to use it. And in fact, that H is SR, then we know this is drop the perpendicular. U is the velocity at infinity. And that's the constant angular momentum divided by the mass. And perhaps we'll make a mental note of it, because we know this is B, so it's B times the speed at infinity. It's something I'll just use elsewhere. It's worth making a mental note of. And this was for the particular case. What's the maximum speed? Maximum corresponding to the point of closest approach, or on the hodograph, this point, minimum is at either of the tangents. Now, we can easily identify the orbital parameters now. That's our H again. Radial motion, we just write the equation for the radial motion. This kappa is the force constant, or the constant for the potential, and it's negative in the attractive case for a pair of particles. Product of the charges divided by 4 pi epsilon naught with a minus sign. The point of closest approach, of course, if we draw our hyperbole, is just a times epsilon minus a. So that's the distance there. You see that very clearly. Yes. Yes, for example, that's the distance of closest approach. Then that's this a times epsilon minus a. Oops, let me just move to here. Now we just solve and substitute, and then everything falls into place. We get our parameter a, get our parameter b, which is h divided by u. And of course, the maximum value of the momentum, which I shall use later on, is then mass times h, which gives us magnitude of angular momentum divided by the distance. Other things, everything falls into place very nicely here, but we have to put the absolute value on the interaction constant. Now, what is the link between the two approaches? Now, following Maxwell, we've defined it in terms of orbital elements. So our hodograph consists of lengths, but in Hamilton's, it consists of velocities. You see, we work with, in Maxwell's approach, we work with lengths proportional to velocity. And the constant is this h divided by 2b squared, which is a constant. And we want to compare the two, we've got to put in the constant of proportionality. So there's Maxwell, that was what we had from him, multiply it by this factor, and we get that for the gravitational case. And then we read in Hamilton's paper, the hodograph is a circle of which the radius is the attractive mass divided by the constant double areal velocity of the orbit. So you see the two are identical in effect. And Hamilton in his paper renames this, he declares that the Newton's law of gravitation could be renamed the law of the circular hodograph. That's what he renames that law. Now, for the repulsive case, it's really the mathematics or the algebra is identical, but for the plus sign in this case, because the distance is measured from the conjugate focus. So we need to put a plus sign here. Now, instead of maximum momentum at the point of closest approach, which you would call either perihelion, but that's astronomical. I mean, the closest approach to the sun is really periapsis, mh divided by that factor. The rest looks very similar, except kappa is kappa. Now it's a positive quantity. So all of these things are identical. Again, h is b times u, worth noting. Now, the last time we've talked a bit about Hamilton in the broader sense of his many contributions in classical mechanics, in wave theory, optics. He was very prominent in his research in wave theory at a time when the English did not approve of that, but he was an Irishman. The English were dead set on the corpuscular theory because that's how they interpreted Newton's optics. And it was owing to the French. The French took up Thomas Young's work with enthusiasm, whereas the English had rejected it completely. Famous English scientists like Brewster rejected it completely. But Hamilton took this up and he predicted the conical refraction, which I discussed briefly. And it's interesting that it was discovered in the same year by Humphrey Lloyd. So Hamilton made the prediction that you would not be able to obtain this result from the corpuscular theory. But Humphrey Lloyd, again in Ireland, discovered the conical refraction. And I always think to myself, well, that's a mark of a very superior kind of theoretician, can predict something that is found later. And I think in, well, the previous century, I think of Wolfgang Pauli giving his lecture in 1934 on the positron, not the positron, but the neutrino in Princeton, and the neutrino is discovered more than 20 years later. I should also add that there were 2 lectures given on the same day. The other was by Paul Dirac, predicting his magnetic monopole, which we're still waiting for to be discovered. But the reason for putting this up is to refer to other work of his, and that was his so-called eccentricity vector. It also applies to these potentials of our inverse R, or forces inverse square. It's 1 upon the same kappa constant, velocity times angular momentum, plus this is R upon R is, of course, the magnitude unity. It's a conserved quantity. I'd like now to look at this expression and see what one could do with it. Now, first of all, well, we'll just note the 2 that kappa can be of either value. If we have an electron near a nucleus, it would be this expression in terms of atomic constants, h bar squared divided by times the charge on the nucleus, or the charge number, divided by the electron mass, the scale length being the Bohr radius. But if you work it out, and you could do drawings, I will not show all the drawings, you'll find out that the direction of A is along the principal axis of the conic section, the one joining the principal focus and the conjugate focus, and it points away from the perihelion, or I should say periapsis. Now, if we form the scalar product here, just form the scalar product, and then we'll collect the terms, and what we find here is this is precisely the value of the eccentricity which we've derived a few slides ago. So really the magnitude is the eccentricity. There's something else one could do with this by reversing this, changing the expression slightly, just rewriting it, because I'm interested here in what about a momentum hodograph? If we're going to take these ideas, it might be, certainly from a quantum mechanical point of view, the momentum is the fundamental quantity rather than the velocity. So let's think of whether we could construct a momentum hodograph. We change the expression to this form, and now we form the scalar product with itself. And do this carefully. Now, there's the interesting thing is this points along now the principal axis x, so we know its magnitude is eccentricity. Orbital angular momentum, the 2 drawings we did last time were the same trajectory where the center of force is either the focus or the conjugate focus. You get plus or minus mass times h times z there. Plus for the attractive case, minus for the repulsive case. It's very important to get these vectors correct. Now, when we collect terms, what do we get? And lo and behold, this is a circle. So the momentum hodograph is once again a circle. We haven't done it with the beautiful geometrical constructions. This is just a piece of easy vector analysis. And what is very interesting here, that's why I say get the signs absolutely right, because for the attractive case, this kappa is negative. That means there's a plus sign. For the repulsive case, it's positive. It's also a plus sign. So therefore, the center of the circle is displaced towards the negative side, negative value of py. I've made rather rough drawings of this, but here we have the case. So the question is, let me just word this. I should say the radius of the circle, of course, is kappa divided by h. It's displaced by epsilon time. So it's the question about the displacement of the center is either the radius times a number that's greater or less than 1. Or in fact, could be 0 in the case of the circular motion. So here we have it. So the ellipse, its displacement is less than the radius, sits like that. And this is the complete circle. For the parabola, of course, epsilon is 1 and it sits here. So it starts at rest at infinity, it's attracted in, and it just manages to reach infinity again if we're in the ideal case. But in the case of the hyperbola, where epsilon is greater than 1, we're farther away than the radius. And what I should like to show you is that if one draws the tangent angle here, phi, it's in fact 90 degrees, pi upon 2 minus half of the angle between the asymptotes. So that means that the motion is confined from one point to the other. In the case of the attractive motion, we move around this way. If it's repulsive, we move around the upper edge of the circle, which will sound familiar if you look at our two diagrams from last time. Now, I mentioned just said we should take a mental note of these two that we derived from the formula. Their difference is here. And we just rewrite that. That's exactly what we had in the diagram there. 2 kappa upon h is the difference between the two. And the tangent angle is arc sine of 1 upon epsilon, which is the cotangent of this expression here. And pi minus phi upon 2 is the cotangent, because phi upon 2, as we've seen last time, is the arctangent of b upon a, so these two are identical. So that's the complementary angle to the half angle between the asymptotes, which is there. And so that was, therefore, we see the momentum hodograph in the case of repulsion lies on the arc of circle of radius that's kappa upon h and subtended by this angle, or 2 pi minus that value. So this is precisely what this diagram then represents. It's either that or it's that. It's not the complete circle, except in the limiting case of the parabola. Now, yes, and this is fact from last time. That was from Maxwell's construction. And you see, now we've used Hamilton's ideas, not Maxwell's, and we've come to exactly the same conclusion about what constitutes the hodograph in the case of free particles. This is identical with what we've just been discussing there.
Can you say that again? I didn't understand. What's for free particles? What's talking about?
Well, for free particles, the hodograph is not a complete circle. That's what we proved here. We proved it two ways. We proved it last time, and we proved it here using momenta and using Hamilton's so-called eccentricity vector. I'm rewriting it and squaring, and we found a circle, but the fact that it's a circle doesn't prove that the momentum moves along the entire circle. It moves around a limited part of the circle, limited by the two tangents. And the tangents are drawn at the asymptotic directions. And we've proved there that the asymptotic directions are complementary to the tangent, tangent angle phi. So that means
I was just surprised because you said free particle, and then I thought, no, the free particle, like there's no interaction. So you're talking
about particles that are not bound.
But if you take this case of the free particle, the absolutely free particle, then it's just a point. Velocity is just
yes, but the absolutely free particle does not have this interaction potential. So
I'm saying, I understand. Yes. So it doesn't follow you cannot say it's still part of the holograph. Maybe about point.
No, well, what you're wanting is a holograph that corresponds to a straight line. I mean, there's no interaction. The thing follows a straight line. So these things should collapse then onto a straight line. Now, what other types of potentials? Just to mention that one could apply some of these ideas. For example, I discussed last time the interaction between an energetic charged particle in a plasma and an atom in an electric field, which simulates a permanent dipole. So that would be the potential here. one determines the turning point, and the condition for spiraling is very clear classically. And so the hodograph then would be an outward spiral, which commences at a distance proportional to the speed, and it spirals outwards. Instead of the particle spiraling in, it spirals outwards. I've artificially, as I explained last time, completed this trajectory by having it collide with a hard core and then leave again. So one half of it comes in here, spirals in, eventually it hits the center of force, where it would remain if it were held there. But if we just assume that it's a hardcore collision, then it comes out again and completes the trajectory in that form. We've also discussed last time that now the rho there, I should have said, was the impact parameter. Impact parameter would be the distance from the center of force. So this is the rho in this case, which is 1.2. If the particle did not, as Thomas's last question, particle had no interaction, that would be the, if this were purely passive, that would be the impact parameters.
Would that be eccentricity infinity?
Well, no, but we're not talking about a conic section motion at all now. This is a totally different thing. It's not conic. You see, that the previous treatment of Hamilton and Maxwell is entirely limited to conic section motion. And that's the difficulty with Maxwell's approach, actually. Thank you for anticipating that. It's limited by the fact that we, beautiful as it is, it builds on the elements of the conic section motion, which we described last time is only applicable to an inverse square force law. So it's meaningless to talk about these things in this case. One has to analyze this trajectory from scratch, and it's convenient to have the particle entering at an angle theta equal to naught, and the vector turns around, and then I could call that phi. That was the angle corresponding to the periapsis, which is the point of closest approach, and then it moves around. If you maintain, in terms of these parameters here, rho greater than that, we just have one passage around the center of force. We also last time showed that if you fall below this value and you're not spiraling, you could have several passages around the center of attraction and then the particle escapes. But it's totally different from gravitation, where you're limited to the conic section motion. Now, what we would do here is just go through the analysis. So that's orbital periapsis is that's the value here. Periapsis angle, you can substitute from here. You find that into the angle. Here you find that the angle is equal to phi then for the distance for the point of closest approach. The incoming branch, this is just simply a simple analysis from that law of interaction. The outgoing branch would look like that. The radial distance is in this form. It's actually this is a very easy case to analyze for oneself, which is fortunate. Now, velocity, you take the derivative, but be careful because the unit vectors, the unit vector that you deal with is time dependent. So the unit vector r dot time derivative is theta dot theta unit vector. So, and theta dot is minus the unit vector ddt thereof is minus theta dot times r. You have to be very careful. When you're not working in Cartesian coordinates, beware of the unit vectors. They change their nature as a function of time. Deviation, so velocity does not correspond, of course, to the radial direction. There's a deviation from them. But if you now determine the acceleration from here, one will be very pleased to find this, in fact, is along the radial direction with a minus sign. That was an attractive potential. So indeed, the acceleration, the force is radial, the acceleration therefore agrees with Newton. It must be radial also. Need these very much need to be careful here in order to obtain that relationship. Now, I've just tried to draw this case. Here's our trajectory, and this is just an analytical plot of velocity. This is the Hodograph, or shall we say the Hamiltonian Hodograph would look like this, where we're working, just plotting velocity. And we can check that. You see the maximum value of the speed occurs at right angles to when the particles reach this point, which is exactly what we would expect. And we could check again by drawing a few tangents that the acceleration, here we see the acceleration is indeed anti-parallel to the radial vector. And a few others here, I just put them in for illustration. Acceleration here's the point, corresponding point. We go a bit farther, the acceleration tangential is opposite to the radial vector, which is out there. You can check it at every point. But the Hodograph, again, does not complete, naturally, it's not a complete closed curve. As you see, in the case of the free particles, the special case we discussed, inverse square law, it's also not a closed curve. So the Hodograph is not a closed curve when the particle is free. But that's a very simple case to analyze. Very simple. So,
is this still a circle, or is this a...
No. This has nothing to do with that circle. This is here. Look at that. Look at the form. That there. I mean, let's see. So H. Yes. No, because you see, the denominators here are different.
Okay, so this is not in that sense. So you said this is a
open curve. Yes, I would call it that because it's a velocity momentum Hodograph.
Okay, but it's not the Hodograph that we saw before. The Hodographs before.
No, because they were for the inverse square law or the inverse are potential.
Then I didn't get this. So for what potential is this now?
Oh, this was iron permanent dipole, so the potential is inverse r squared, the force therefore inverse r cubed.
Then we get a segment of an ellipse. Is that an ellipse?
No, it's not. It's neither the one nor the other. You can't. I don't have a word to describe what this is, but it's very easy to calculate. So now I wanted to leave this idea in the hands of the listener to take this into the study of trajectories in, say, plasma physics, cosmology, particularly interested in particle physics, quantum mechanics. Can one take this idea into microscopic physics? Now, I would mention an interest in the momentum in the case of atoms is the following, that the momentum representation is often very much more practical and useful. I'll give you some examples: collisional ionization, collisional excitation, where what counts is the momentum transfer. And therefore, working with wave functions in a momentum representation, wave functions that are explicitly functions of momentum are very useful for such calculations. Now, for a certain given problem like transition probabilities, you can prove that you could calculate them in our more familiar coordinate representation. You could also calculate them in the momentum representation. You get identical results for transition probabilities. But these, it's very convenient in some quantum mechanical problems to use momentum. And this is just an example. We're familiar with this. Let's take the 3s orbital of hydrogen. Well, here it is in the momentum representation, where our atomic unit is the inverse of the Bohr radius. There, this unit is the Bohr radius. And of course, the wave function over here near the origin, of course, corresponds to the highest value of the momentum. That means these things look very different from each other. And it also is true that in problems where you have many electron atoms, the difficult part of the calculation is usually associated with the points closer to the origin. And the easier parts are where the momentum is the smallest. It might be more advantageous to then work with the momentum when one is working in a region closer to the origin. Now, we say we would like to look at the momentum representation. I should say, first of all, here, refer to, this was an attempt to take well, what it was that paper. It looked in fact, a lot of detail at Pauli's work. Because Wolfgang Pauli took this eccentricity vector of Hamilton and he turned it into a quantum mechanical operator. And the question is what one could do with this. And Pauli derived a number of very, very useful results, and that's his great paper, I called it in 1926. And I found ways of using this, which were very illuminating, shall I say, using Pauli's work. And one of the nice things that came out of this was a very efficient algorithm for transforming from spherical polar to parabolic states. So you need an algorithm to get the transformation coefficients. They come out beautifully by using the quantum mechanical A, and that's there. I've checked it against other algorithms. I found I was very pleased to see how efficient that was. But now going into the quantum mechanical side, if we're working with a momentum representation, it's somewhat unfamiliar to us, perhaps. Coordinates now take this form. Momentum, of course, is P. Angular momentum takes this form, and we can work our way down the line. The warning here, I always think it's worth warning people that this can be misleading if we're not using Cartesian coordinates. One might be tempted, for example, to say the radial momentum is minus IHDDR, but that there is not a Hermitian operator. If we take the equation of motion, R dot here, we work through that PR there, capital PR, that's the conjugate to the coordinate. Momentum conjugate to the coordinate R is this little PR, which is just minus IHDDR minus that, and you show this one is Hermitian, that one is not Hermitian, so it's not really the suitable operator to work with. But you have to be very careful. You come in different coordinate systems, you frequently come across that. We learn these things mainly in Cartesian coordinates, and it's the simplest case to deal with. Now, I have no idea to what extent one can apply, because I haven't yet attempted to do so, the quantum mechanical eccentricity vector, we want to call it A, it's not an appropriate name, to take it into other areas. I have no idea with what success, because I've stopped at a certain point, and any reader can, I say, very welcome to continue this. And it's a very interesting idea to me, and then to try and take that and then go to a semi-classical approach and see whether it leads back to the Hodograph. You could do it backwards. So start with the quantum mechanical operator, do the full calculations, and then go over to the case where we saw last time the orbital angular momentum is large, and then you approximate closer and closer to a classical trajectory. See what could come from that. But I leave this in my listeners' hands, and I started with a quotation from Blaise Pascal.
I just wanted to ask, so do you use this quantum mechanical version of the eccentricity?
Yes.
So the eccentricity operator?
Yes, that's...
Do you use that to make a transformation from what?
Well, spherical polar, you might... I was interested in parabolic states because these are the start states in the plasma. So, perturbed atom might be perturbed by an electric field. And then you have different sets of quantum numbers, and you need to transform. Perhaps in calculations, it might be convenient if you have the transformation matrices to work in a more familiar wave functions and transform these. There are different uses you can put this to. Now, I started last time with a quotation from Blaise Pascal, and I'd like to, because I'm very conscious of the passage of time now, and would encourage my younger listeners to work through some of these ideas for themselves. For this reason, as Blaise Pascal said, people are generally better persuaded by the reasons which they have themselves discovered than by those which have come into the mind of others. Meaning, I think that what we learn by teaching ourselves makes a greater impression on us than what we learn by sitting and listening to someone else. And at this point, I shall stop. Thank you. Yes, indeed.
Thank you. So, if I understand you correctly, we have the picture of the ellipse for planetary motion. And we have Kepler's laws to describe also the time passage through the ellipse. Now, if I understand you correctly, we can also use the Hodograph.
Yes.
Use the circle.
Yes.
Okay. And then the thing goes on the complete circle around.
Yes. You're not understanding me correctly. You're understanding Hamilton and Maxwell correctly.
Thank you. Through you, sir. And the point is now, do you have some laws like Kepler's laws? Can you say something? I mean, Kepler's laws say everything moves on ellipses or on circles, right? Then it says something about the time.
Also splitting out equal areas in equal times. That's the most important part there.
Can you make that?
Well, just because there's h factor, which is twice the areal velocity, as it's called, it comes through all this analysis. This h is the key parameter to this whole analysis. You see it in almost every one of those representations. It's there.
Okay, so how does the vector sweep around? I mean, how does the velocity change time? Can you say something about the area that is swept equal times? Or?
Well, you've got that built in the constancy of h into that. But remember that the momentum is not measured from the center of the circle. That's where the subtlety comes on. It's from the origin of the coordinate system. But that is not we don't have not an explicit time representation. You have to work that out as to where it's pointing at a given time. With Maxwell, it's very easy because you can work out how the coordinate is oriented at a given time. And that gives you the corresponding point on the Hodograph automatically, because Maxwell links the two together. With Hamilton's, it's more of a static representation. We're not actually looking to see where the coordinate is at the point. So that, in fact, is a point where Maxwell's is a more, I keep saying German, anschaulich approach.
This is
I'm talking about, like, like visualizing these motions in this different way and how quite beautiful the geometry becomes. I mean, it really gives you that feeling of why this three-body problem is such a conundrum for us.
Yes.
And I'm wondering, like you're talking about how when you come closer, if you've got multiple electrons that are coming closer to the nucleus, how momentum is maybe a better space. So I'm wondering if some of these transformations can't help to somewhat understand this three-body problem. Of course, it's a very, very complicated problem, but whether it couldn't add to some progress to that problem.
Perhaps that's a hope. But we did mention of all, I mean, the original inverse square representation is limited so much by even any relativistic effects take you away from that, apart from 3-body, 4-body interaction, which can only be done iteratively, never exactly.
And it's so unpredictable. Yeah.
It's you would have to choose the level of approximation which is suitable to the problem. That takes judgment.
But it practically makes you feel like kind of suddenly really understand why this 3-body problem is such a problem. But lucky for us, almost all interactions you can simplify to pairs of bodies. So lucky for us, a lot of problems
Yes.
actually think about them not
Yes.
all by all.
Yes, and then in purpose, we often, in order to do that, use this trick of divide shielding,
Yes, exactly.
Yes.
Exactly.
which is only an approximation.
So building on what you said, in the 3-body problem, celestial mechanics, we use the principle of the osculating ellipses. That means at each point of the orbit, we fit the ellipses that is just the same tension. It's kissing on.
Yes.
It's kissing
Yes.
ellipse. What would you do? Do you think something like that happens to the holograph as well? That if you have perturbations, either in the 3rd body or a non-spherical,
Almost certainly we would find something analogous.
yeah, and then you could do a kind of perturbations here.
But I now invite you to take it further.
Thank you very much. And you can find these different kind of so periods. No, there are short periods, long periods, and secular patterns. Maybe it gets easier.
Would be
That would be fantastic.
assume that. Thank you
Yeah.
very much for
Yeah.
the comments, which I shall refer to. But I'm really interested to look at that in something.
Yeah, and I just add to it, the problem with the usual perturbations is that for high eccentricities, the series that describes the time of comparing elements is divergent. So it diverges. Maybe here you have a better chance. I mean, if everything is on a circle, it's small eccentricities. So maybe your perturbations here is converged much faster. In which case you can do all the Russian orbits of satellites because they have high eccentricities. They use because it needs less control.
Thank you very much for that. That's very interesting.
Thank you very much. Thank you, the speaker.